Okay, so going to try and help with the organic analysis, mass spectrometry and infrared spectroscopy part of the course. So going to start off with mass spectrometry, and hopefully at the end you'll be able to explain why multiple molecular ion peaks form in a mass spectrum, and also why there are not just those molecular ion peaks in a mass spectrum and what benefits that can give us when we are using our mass spectrums to try and identify our compounds. So we've already looked a little bit at our mass spectrometry right at the start of the year when we were doing our atomic structure topic. So the type of mass spectrometer that we looked at then was the time-of-flight mass spectrometer. And this type of mass spectrometer uses the time it takes during that flight tube. So where that flight path is labelled, that section of the mass spectrometer is the flight tube, and that's where they record the time it takes for the different ions to travel to reach the ion detector. So we looked at why we use mass spectrometers, so in order to determine the mass of separate atoms or molecules, and we also discussed that forensic scientists can use mass spectrometers in order to help them uncover what they are after. We looked at the 6 stages of the time-of-flight mass spectrometer. So the vacuum is the first stage, so all of our mass spectrometry is carried out in a vacuum chamber. Give you a moment to think about why that was. So vacuum, we're talking about carrying it out without any air particles. So those particles could be, they could get in the way and therefore slow down our ions if they were to collide with them, and therefore impacts on those results. So carrying it out in a vacuum means that those air particles won't be in the way as the ions are travelling through the spectrometer. Ionisation is the next stage, so either the atom or molecule that we're using becomes ionised. In this case, we're talking about either electrospray ionisation or electron impact ionisation. In both cases, we're removing electrons, and so we're forming positive ions. Thinking about why that was again, just give you a moment. So our ionisation is crucial to our following stages, as in 2 stages actually. So our next stage, our acceleration, where our ions are accelerated to higher speeds. By having our ions as charged particles, that means that they are able to be attracted to something that is negative. So that's how we accelerate those ions, is using charge differences to attract those positive ions and make those ions travel faster. But of course our acceleration is mainly to get those higher speeds and separate out those different sized ions. So our heavier ions travelling slower than our lighter ions, and then we allow those ions to drift in the flight tube until it reaches the detector, and we're recording that time of flight in the flight tube until it reaches the detector. On detection, our positive ions pick up an electron from the detector, and the flight time at that point then gets recorded. So this is the second reason why it's important that we have our ions, so that we can pick up those electrons and complete a circuit in order for that signal to be generated. So our analysis, that signal from the detector is passed to a computer, and that generates it into a mass spectrum, which is where we come in to have a look at those. So we looked mainly at mass spectrums of atoms and elements, as we were looking at isotopes at that stage. So you can see an example of a mass spectrum here, where you've got your relative abundance, so how common that isotope is, compared to the mass charge ratio at the bottom. However, as we mainly form singly charged ions, then our charge is just +1. And so when we're doing mass divided by charge, you're dividing by +1, so your x-axis is effectively just the mass of that ion that's reached the detector. Isotopes, just a quick reminder that they're where we have the same number of protons but a different number of neutrons, and so that gives us a different mass number. And so when we're doing our mass spectrums, our different isotopes are going to have different signals due to those different masses. So the abundance of each isotope shows in that mass spectrum. On this picture, it's of our chlorine isotopes. So chlorine has two isotopes, chlorine 35 and chlorine 37. Now this mass spectrum tells us two things. The first thing is quite obvious, is that the abundance of chlorine isotope 35 is a lot higher than the abundance of the chlorine 37 isotope. But if we look closer at the numbers of the relative abundances of each of these isotopes, we can actually work out the ratio between them and see that it's a 3:1 ratio between the 35 and the 37 isotopes. So we looked a little bit at molecules, in particular diatomic molecules, in how we can calculate the abundances of those. So it's all based on probability, which you might have come across in maths. So in maths, when we do probability of x and y, then we times those probabilities. So in this table on the right, we've got the various different combinations that we could have for a Cl2 molecule. So the 4 different options there, depending on which isotope is present. You'll notice that the 2 in the middle, they have the same abundance, but also they're effectively the same molecule. But in terms of organising and probability, we do have to write them separately to show that A could be 37 and B could be 35, or A could be 35 and B could be 37 as those 2 options, but actually they give us the same relative molecular mass, and therefore the probability of each of those is actually also the same. So we've calculated those abundances, and then when we would draw our mass spectrograph of those, we'd expect that pattern to follow. Obviously combining those 2 in the middle, the 18.75, would therefore double as we combine those 2 middle ones. Notice also that the percentage abundance, it all adds up to 100, so that's a good way to check that you have done it right, is that they should all add up to 100%. So here we've got the mass spectrum of chlorine molecules, so Cl2, and you'll see that Cl35 is still the highest. That's because of that higher ratio that we saw there, 56.25%, still larger than the combination of those 2 18.75%. But those 2 18.75% are now added on top of one another in the middle for that MZ72 peak, and then a little one for that MZ74. So when we're talking about organic spectroscopy, we're talking about organic molecules, and therefore we're talking about molecules which contain carbon. And so the isotopes that we really care about for these is going to be our carbon isotopes. So the 3 carbon isotopes there are carbon 12, carbon 13 and carbon 14. However, when we're doing our mass spectrometry, we only really deal with carbon-12 and carbon-13. There's carbon-14, there's only trace amounts, so they never show up in spectrums. Carbon-13 is only actually about 1% present in compounds, so it's only a really small peak in our spectrums. It will always be that 1 unit to the right, as it is that 1 unit in mass higher than carbon-12, but as carbon-12 has that 99% abundance, that is the main peak that we're drawn to when we look at our mass spectra. So fragmentation is something that's quite new, but as the word sounds, it's the process of breaking our molecule up into fragments. So that happens as our bonds are broken. So that can happen to our chlorine molecules. So Cl-Cl bond breaking, we're just going to end up forming our chlorine atoms. So you'll see now a larger image of the one that we saw before. However, this is now showing us that lower end of the spectrum, so that we can see those chlorine atoms, both the 35 and 37 isotope could be formed, and so they're also now included in that mass spectrum. In our organic molecules, we want to consider how easy it is to break our bonds. So any bond can theoretically be broken, but some are more likely to be broken than others. So if you look at your bond enthalpy on the right hand side, you will see the CN and the CO bonds, for example, they are much more likely to break and leave our carbon positively charged, whereas our C double bond O, that's a very strong bond, and so very unlikely to break. Also our aromatic rings, so this is our C6H5 it's a hexagon with a circle in the middle. We look more at those next year, but again it takes so much energy to break those rings that in mass spectrometry they pretty much always stay intact in the spectra, and so that's quite a good identification that that is present, as that will always be a fragment ion peak in the spectrum. So what fragmentation can help us with is about the structure of the molecule, because it can tell us a bit about the connectivity between each of the groups, say, in the atom. As we know that some bonds are more likely to break than others, we can start to piece them together by looking at the fragments and the masses of those fragments. But in terms of the abundance of these fragments, you'll see in a moment that actually the fragment ions can sometimes be higher than the molecular ion peak, and that's because it depends on how the fragment is formed, because if there are lots of ways in which the fragment can form, then they will be high in abundance, but also if the ion is more stable than the molecular ion, then that is also more likely to form and therefore be higher in abundance. So want to look at an example of pentane, so C5H12, and the CC bonds can be broken, all of them, and so we get a variety of fragments that can be formed. So if you break it between the first and second carbon, then we end up with our CH3 peak, which is our MZ15 on the far left hand side. If we break between 2 and 3, then we get our 29, sorry. Breaking between our 3 and 4, we get our 43, and between our 4 and 5, we get our 57. So notice that the base peak has been labelled, so that's the 43, and that's the tallest peak in the spectrum, and it's for the most abundant fragment ion. In this example, that's the peak that you would break either 2 to 3 or 4 and 5 to get that molecular ion peak. So you're looking at the more frequent ways of making that molecular ion peak. So here's an example question. So compound Q has the molecular formula C4H7ClO. It's a volatile liquid, and the mass spectrum of Q contains two molecular ion peaks at MZ106 and MZ108. It also has a major peak at MZ43. So 2 parts to this question. The first part is suggest why there are two molecular ion peaks, so the ones at 106 and 108. And then secondly, the fragment ion produced from Q has MZ43 and contains 3 different elements. Identify this fragment ion and write an equation showing its formation. So if you want to have a go at this question, I would say pause the video. I'll go through part A and then through part B, but obviously if you want to have a go at it yourself before listening to the work through, then do pause the video before I move on. So looking first at part A, why there are two molecular ion peaks. This is going to be because there are two molecular ion peaks due to the two isotopes of chlorine. So whenever we've got multiple ion peaks, that's always because we've got isotopes involved in our compound. In this case, they're a result of our chlorine, so that's Cl35 and Cl37 isotopes that we looked at earlier. Question for you to also consider, which I'll come back to after we've looked at that part B, is why is it the isotopes of chlorine that's causing these molecular ion peaks and not the isotopes of carbon? So looking now at part B, so part B, just a reminder, is looking at the fragment ion produced from Q has MZ43 and contains 3 different elements. Identify this fragment ion and write an equation showing its formation. So the first thing we want to look at here is thinking about the elements that we have in that molecular formula. So the carbon, the hydrogen, the chlorine and the oxygen, and what those molecular masses are. So carbon is 12, hydrogen is 1, chlorine is 35, and oxygen is 16. So when we are thinking about forming a fragment ion MZ43, if we were to use chlorine as one of those 3, we would be very limited in what else we could combine it with. Because if we subtract 35 from 43, we're only left with 8. So theoretically, yes, we could use hydrogens, but actually we only have 7 of those, so we'd be left 1 short. And we can't use carbon because that's bigger than 8, and we can't use oxygen as that's bigger than 8. So our 3 different elements can't therefore include chlorine. So we've now deduced that it must be a combination of carbon, hydrogen and oxygen. So now we need to work out the numbers of each of those. So because we know that it must have at least 1 carbon and 1 oxygen, we can subtract those. So 43 minus the 12 for the carbon is 31. 31 then minus the 16 for the oxygen gives us 15. And 15 then nicely correlates to that CH3 15 peak that we looked at earlier on. And so by taking that step by step, knowing that we have 1 carbon and 1 oxygen, then looking at what is left. So that 15, well, we know it can't be another oxygen because there aren't any more, but also oxygen is 16 and 15 is obviously smaller than 16. So the only elements that it could possibly be is that combination of carbon and hydrogen, and 12 plus 3 gives us that 15 that we need. So our molecular ion peak is therefore that CH3 plus the 12 that we initially took off that carbon and the 16 that oxygen, remembering the square brackets and the positive charge, as it is a fragment ion. So the equation to show its formation, we've started off with the molecular ion, as that's what is formed in that ionisation right at the start of the time-of-flight spectrometry. We're then breaking that apart, and so we formed our fragment ion, and what we're left with is those remaining carbons, hydrogens, and the chlorine. So another question for you to be thinking about here is, why would the C2H4Cl not be detected? So in a moment we're now going to come to the second question that I put underneath part A, the why is it that the isotopes of chlorine and not the isotopes of carbon that were causing those molecular ion peaks. So the reason for that is because the difference in those MZ values is by 2 units. So 106 to 108, we have to go up by 2 units. And that's the same difference as there is for our chlorine units, so going from 35 to 37, whereas our carbon isotopes, carbon 12 and carbon 13, only differ by 1 mass unit. So these ion peaks can't be a result of these isotopes, as it would need to be at 1 mass unit intervals. But also because we have 4 carbons in this compound, it becomes a lot more complicated in the different combinations that we could have. So you'd have a lot more than those 2 molecular ion peaks as a result of carbon isotopes. So the next bit we're going to look at is the why the C2H4Cl is not detected. So this is because it's not a charged particle, and so if it were formed at the end where we get to the detector, as it's not charged, it doesn't pick up the electron to complete the circuit, and therefore we don't get a signal generated, and so it won't be present in the spectrum. However, we could form the ion of C2H4Cl, maybe less likely to form and so lower abundance. However, if that ion was to form instead of the other fragment ion, then that would be detected if it were charged. So this is compound Q. I've rotated it slightly to try and draw it how I would normally draw it on the whiteboard. So I always draw the oxygens going upwards, but we can see where that break would happen, so that you've got your CH3 group here and your CO group there. You're then breaking up between the 2 carbons, which each have 2 hydrogens on, and that chlorine atom there. So question to take away is for you to be able to explain why multiple molecular ion peaks form in mass spectrum, and why there are not just the molecular ion peaks in a mass spectrum, and what benefit those non-molecular ion peaks can give us when we're looking at our organic analysis. So the next section we're going to look at is infrared spectroscopy, and hopefully by the end of this we'll be able to explain how you could distinguish between the functional group isomers that have a molecular formula C5H10O, and how you could confirm that a sample was an exact match of Pent1N2O. So to start with, we want to think about our bonds. So our bonds between atoms, they are constantly vibrating. So when you picture a bond, I want you to picture a spring with 2 balls at each end and them going back and forth. So if you were to stretch a spring, let it go, and it would oscillate back and forth, back and forth. So your bond's being stretched and compressed constantly. Each bond vibrates at a unique frequency. So different types of bonds will vibrate at different frequencies. Stronger bonds vibrate faster and therefore have a higher frequency. Infrared radiation, which we should know from GCSE physics, is part of our electromagnetic spectrum. So you can see it there, it's used in remote controls, but in chemistry we use it for infrared spectroscopy. So our infrared wavelength is between 700 nanometers and 1 millimeter, and that corresponds to 430 terahertz to 300 gigahertz. And this frequency is the range in which bond oscillation frequency also lies, and so that means that our bonds can actually absorb infrared radiation. As a particular bond has a specific frequency, it can only absorb radiation that has the same frequency as its natural frequency. The other frequencies are not absorbed. So it's a bit like with colour filters. So they absorb any colours which are not made of it, and then the others are passed through and seen. So here we've got a yellow filter, so that will absorb the blue light, so it keeps hold of that blue light whilst letting through the red and green light, which together make that yellow light. But that blue light is not seen because it's absorbed by that yellow filter. So with our infrared spectroscopy, we have our sample, and as we shine our infrared radiation through the sample, the radiation which then emerges is missing the frequencies corresponding to the bonds in the sample. So the frequencies that weren't absorbed by the sample do then get detected, and we can plot the graph of the intensity of the radiation passing through the sample against the frequency of the radiation. Frequency we talked about earlier being measured in hertz. However, when we're dealing with infrared spectroscopy, we use a different unit. So we talk about it in terms of wave numbers and measure them in per centimetre. So wave number is actually the inverse of wavelength, which again you should be familiar to from physics GCSE, and we can link wave number to frequency by the constant speed of light. So wave number is the same as the frequency divided by speed of light, so that's a conversion that the instrument can do when plotting the results of our radiation passing through the sample. You might actually recognise this equipment. So in, can't remember what month, but autumn term, we had an outside scientist come in to talk to you all about infrared spectroscopy. He had, I think it was about 6 different samples, things such as glucose, aspirin, paracetamol, and he had an infrared spectrometer that he'd set up at the back of the classroom, where he ran the infrared spectroscopy, and you then had to match it to the graphs that he already had. I think you might have even been given data sheets and asked to identify some groups, but obviously we hadn't learned about that yet, so you weren't expected to be able to do that. So when we're looking at the graph, we talk about them in terms of peaks. However, what you'll notice is they are actually the dips of the graph. So we are able to use these peaks to identify functional groups present in the compound using those unique frequencies of bonds. Means that we get unique peaks in our graph. So a molecule with carbon and oxygen, it could be a C double bondo or a C single bondo, and these are going to have different frequencies and therefore different wave numbers. So our double bond is obviously a stronger bond, and so it's going to vibrate at a higher frequency and therefore have a higher wave number. Similarly, with our OH bonds, depends on the environment that they're in. So it could be part of a carboxylic acid group, or it could be part of an alcohol. Now, we know our acids, they like to lose their protons, and that already signifies to us that that OH bond in a carboxylic acid is weaker than the OH group in an alcohol. So our alcohol OH group is obviously a stronger OH bond and therefore has that higher frequency and higher wave number. All of the absorption numbers, so the data that we need when we're talking about these in answering our exam questions, are in the insert that you get in your exams. I've put this in the team's class materials folder, but it is also on the AQA website when you go onto the assessment resources, so you could also find it there. So this box in red is what's called the fingerprint region. Now, it's called this just like with our fingerprints, they're unique to us. For a compound, that is its fingerprint. It's unique to that compound. So there are many peaks in that region due to complex vibrations, and that is because it's unique to it, it can be exactly matched to a known sample in a database. So we can use computers to overlay them and make sure that they match and then confirm its identity. But if they don't match, then it's going to be potentially an isomer of that. So it could still be the same functional group, but maybe a positional isomer of that compound, because the complex vibrations are going to be different in those different isomers. Greenhouse gases, we talked a little bit about when we were doing haloalkanes, and we looked at the ozone layer, and then we started to look at alkanes and combustion and carbon dioxide and methane, both being greenhouse gases. Also looked at greenhouse gases at GCSE, and what we know there is that the infrared radiation that's emitted from the Earth as the Earth heats up from the sun, that gets absorbed by our greenhouse gases and then re-emitted back down towards Earth. Now, the reason why they absorb this infrared radiation is because their bonds are absorbing that infrared radiation due to their frequencies being in that infrared region. So our bonds are absorbing the greenhouse gases, the bonds of the greenhouse gases, absorbing the infrared radiation. Our carbon dioxide, for example, has two C double bond O's, each of those bonds absorbing in the infrared region, as we've seen when we were just comparing C double bond O to C single bond O. Per molecule of CO2, we have quite a low greenhouse effect, but due to the amount of carbon dioxide in our atmosphere, that's what's making it a problem. So the high number of those CO2 molecules in the atmosphere is causing that enhanced greenhouse effect. Methane, again another greenhouse gas that's causing a problem. Whilst it's lower in concentration, so fewer molecules in the atmosphere, it has a much higher effect per molecule of methane, and so still quite a significant problem. Third main greenhouse gas that we talk about is water. So water is again quite a powerful greenhouse gas in that per molecule of water it has quite a high effect on the greenhouse gas, but our concentration of water molecules in the atmosphere obviously varies, and so direct comparison isn't as easy. So a few questions now to look at. So just as before, pause the video, have a go at it before then listening to the work through. So this question here, compound X has the molecular formula C5H12O and is a secondary alcohol. So one feature of this spectrum which may be used to confirm that X is an alcohol. So when doing these questions, make sure you've got that data sheet in front of you. You get given it in your exam. So just like you'd have a periodic table in front of you, by all means have this infrared absorption data in front of you. So our alcohol has a peak in that 3,230 region. So this peak here corresponds to the OH bond found in alcohols. The one to the right of it here, so where it's got that dip, that's due to CH bonds. So CH bonds obviously very common in organic compounds, so you will see this one quite a lot. However, it's this higher up one here that's due to that OH bond in alcohols. So now we're going to go through 3 different infrared spectras, and we've got 3 different compounds that we're going to be trying to identify from these spectras. So compound A is a dibromoalkane, compound B is a diol, so an alcohol, and compound C is a dioic acid, so carboxylic acid. So what you should have hopefully picked out there, obviously pause the video if you want to have a go first yourself, but both compound B and compound C, they are both going to be having OH groups, but B has an OH group for an alcohol and compound C has an OH group for an acid. Compound C, we should also be able to find the C double bond O group in our IR spectra, whereas our dibromobutane doesn't actually have any oxygens, so we're not going to see any OH and we're not going to see any C double bond O. So the first one to look at is this one here. So we've got a nice peak here which we just saw earlier, and that's going to be our OH of our alcohols, and therefore it's going to be that butane 1,4-diol, our compound B. This next one here, whilst it's quite hard to see this acid peak, it is actually here. If we jump back to the other slide, you can see that that CH peak, yes, it's got that dip little peak here, but then it's quite smooth up to the top, whereas here where we've got that dip and a little bit there, it's no longer that smooth path up to the top. So this bit here is due to that OH for our acids. It's quite a bulging region because they're obviously at such a similar wave number, they're overlapping a bit. But also what we can see is this C double bond O peak here. I haven't quoted that on the next slide, but it should be in that 1680 to 17 something region. So that main one that we were looking at earlier is that 2,500 to 3,000 per centimetre, which is that OH in acids. And just from that we can identify that it is that carboxylic acid, butane dioic acid, compound C. So process of elimination, we have this one at the end, and already you can see there's no C double bond O, there's no OH alcohol, there is no OH acid, and we can now actually see that unobstructed CH peak around that 3,000 region. So there is only that CH bond peak in that region, there's no additional peaks for any OH bonds, and therefore it's that 1,4-dibromobutane for compound A. I think this is the final question, So using the infrared spectrum below, explain why sample X cannot be, so why that spectrum cannot be of trichloromethane. So here we've got peak around 5, 6, between 700, 800-ish. So that seems to be the only real peak in this spectrum. So we don't have the peak that we've just been looking at, that CH bond peak in the 2850 to 3300 region, and so that means that there can't be any CH bonds present in our sample, therefore it can't be trichloromethane, as our trichloromethane has to have a CH bond because CHCl3. So another question for you, using the data sheet, what would you propose that the peak that we do actually have, so between that 700, 800-ish, what you think that peak corresponds to, what bond? And sample X was produced when trying to make trichloromethane. Obviously they were not successful, but they were doing this via a free radical mechanism from dichloromethane, so CH2Cl2, free radical mechanism, so we're talking reacting it with chlorine with UV light to trigger that free radical at the start. So following those initiation, propagation, and then finally termination step, and it's in that termination step that we're going to be making sample X. I'd like you to see if you can propose a structure for sample X based on that information and the IR spectrum. So I think this is a question I left for you to take away. And then a final question here, another takeaway one. It's the one that we said we were going to be able to answer right at the very start. So I'd like you to be able to explain how you could distinguish between the functional group isomers that have a molecular formula C5H10O and how you would confirm a sample was an exact match of pent 1N2-ol.